So what I'm going to do is just talk about the measurements that are made in climate science and the trends that we're fairly sure of, the things that we're fairly sure of that are happening. And in the atmosphere here then are the greenhouse gases, water, carbon dioxide, methane, things that absorb some of this radiation that's going up into space. They absorb it and then re-emit it back down toward Earth. Now, if we didn't have these greenhouse gases in the atmosphere, it's estimated that the temperature on Earth would be about 60 degrees Fahrenheit cooler. So instead of having an average temperature of around 45 Fahrenheit on Earth, we have a temperature of around 15 below on Earth. This is the Nimbus satellite, part of the SOURCE program, and it measures the incoming radiation. But with these measurements, then, you can do energy accounting. You can do top of the atmosphere energy accounting, or you're just seeing what goes into Earth, what comes out of Earth. And instead of being in perfect balance, there has been a long-term imbalance from these measurements. There's a net accumulation of energy. There's more energy coming in than there is going out that you can measure at the top of the atmosphere. And the amount, the imbalance, has been increasing very slowly year by year. Okay, so energy is accumulating on Earth, and that certainly has consequences. That is a driver, then, of some change in climate. We're looking here at the outgoing radiation from the Earth, the amount of it. And this is the frequency or the characteristics of that radiation. If there were no greenhouse gases in the atmosphere at all of it would go out into space. And that would look like this, a little bit less than this last dotted red line. Okay, so that's what we'd expect if there were no greenhouse gases. You can see in this region right here, the actual amount that goes out into space should be around here, but it's depressed way down here. This is due to absorption of water. It's also due to methane bands, where they absorb light. There's also a water band right over here that's depressing the radiation. This depression is due to ozone. This absorbs some of the light, so the amount going out is depressed. We don't get the full amount going out. And then this is the carbon dioxide band that depresses radiation in this region. So the amount going out here is much less than the amount if we had no carbon dioxide. This band, this absorption band, has been growing year by year, getting bigger and bigger and bigger, deeper and wider. So that is absorbing the thermal radiation that's going back out into space. And therefore, it is one of the main causes of the accumulation, the extra accumulation of energy. The top of the atmosphere measurements say then we have an energy imbalance. We have an accumulation of energy in it. And there are consequences that we expect. The atmosphere should be warming. The oceans should be warming. All that thermal energy has to go somewhere. Some of it, however, will actually not go into warming. Some of it will go into a phase change. It will melt ice. Okay, and when that energy goes into melting ice, the ice melts, but the temperature doesn't change. Both of these will contribute to a rise in the oceans, because as the oceans warm, the water expands. That causes the sea level to increase. And the melting of land ice will cause also more water into the ocean, cause that to rise. Now I'm going to talk about the measurements that are used to monitor global warming. The first is the one you're most familiar with, the average global temperature. And there are big mathematical models and programs that are used where all of this data, over 6,000 monitoring stations, all that data is fed in. And then the programs then calculate sectors, they estimate them, and they calculate an average temperature. And what we see then from these direct surface measurements is we see a fairly steady warming of the atmosphere atmosphere at the surface of the Earth that is increased roughly about 1 degree in the last century. The other way to measure global temperature is newer. It uses satellites that have microwave sounding units in them. And there's been a variety of these satellites since 1978. This is the most recent one, the NASA Aqua satellite. This measures what's called the microwave emission spectrum from molecular oxygen in the troposphere. The troposphere is the first level of atmosphere right above the Earth. This does not measure directly temperature. It measures microwave emission spectrum. Shown on this plot then are these two satellite-based measurements compared with the direct surface measurements, the average of the three things we talked about earlier. And what you see here is just, I think, just a stunning agreement between measurements directly on the surface with actual thermometers or measurements of microwave spectrum where you calculate the temperature indirectly. And you can see they track each other just amazingly well. And this provides verification really for both of them. Pretty strong verification for both of them. So that's the measurement of surface temperature. There are two different methods, on surface directly or satellites. And they fully support each other. The most difficult measurement of all is the temperature of the oceans, because the oceans are stratified. You have thermocline, so you have warmer waters, then gradually colder, then colder, then colder. So it's very difficult to get a good, accurate measurement of the ocean temperature. And that's unfortunate because 90% of all that excess energy we have goes into the oceans. Now, melting of ice. Melting of the great ice sheets, Greenland and Antarctica. The measurements of this have been completely revolutionized by a new system called GRACE, Gravity Recovery and Climate Experiment Mission, launched in 2002. And they launched two tandem satellites. And they orbit in tandem. They orbit together, the Earth in tandem. They're linked by a wireless connection. They're linked to GPS satellites. They're linked to ground stations. And they will detect, as they flow over the Earth, any slight differences in gravitational field. They will detect. So from these slight changes in gravitational field, they can work their way backwards through calculations and calculate the mass of the ice fields in Greenland and in Antarctica. So these are the two big fields of what's called land ice. They are ice directly on land. Here's what GRACE finds. 2002, you see winter, summer, winter, summer, winter, summer, winter, summer, etc. But we also see then a gradually decreasing estimate of the ice from 2002 to about 2004, and then an acceleration. Okay. So the melting of Greenland ice is actually accelerating, according to the measurements of GRACE. Now, when we go to Antarctica, it's the same, except more noise. Starts out melting slowly, and it's accelerating. This is the land ice in Antarctica. This is not sea ice, which is floating ice, but land ice. Now, one last thing. The ocean sea level. We said if melting is occurring and warming is occurring, the ocean should expand, and melting should put more volume in. It should be rising. And this, again, has been revolutionized by satellites. This shows one of the latest ones, the JASON-2, uses an altimeter, so it goes down to the water-air interface, top of the sea, and it measures the altitude. It makes thousands of measurements so it can average out the waves. Okay? So we're getting very accurate measurements of sea level now with relatively low noise. Okay? And again, it's just a steady increase in sea level. Now what about the future? This involves models and projections. I don't know much about these. I know that they try to incorporate everything that's known. I know that they build these models then and then mathematically project them backwards to make sure they fit. Then they project them forward. But all of the models we have so far show a continuing increase in global temperature from 2 degrees to 5 degrees. Now, what does this mean? Well, the difference between our climate right now, which is nice and pleasant, and the last ice age, which was not pleasant, 7 degrees. That's what it took. Don't know what 5 degrees hotter would look like. I don't have a real good sense of what that would look like. But I think, basically, I would worry that two important things would be terribly effective and destructive. One would be agriculture, and one would be water supply. And it takes biology a certain amount of time to respond. If you totally change the environment, and then you've got to bring in a new succession of plants, old plants die off, that takes a while. That takes hundreds of years. We're changing this climate here in a relatively very short time. So anyway, so that's it. That's it for me.